let me start with the review. I'm gonna tell you about the plan for today, and then we jump into the review. Then I'm gonna go with you guys over the proposed exercise, right? Which is this table that I see that most of you are working on. Then we go for the topic of the lecture today, which is like the part 3 of neuronal networks. Okay. Yeah, so like today, as you can see by the agenda, it's a quite ambitious day because I really want to reserve the last lecture for the sort of journal club that I mentioned in the Slack, right? Which I'm gonna give more details in a little bit. But so I try to, based on the articles that you guys listed there so far, I see that there is a lot of interest in convolutional neuronal networks. I think all the 3 articles that are listed there so far, they all use convolutional neuronal networks. And if I knew that you guys had so much demand for it, I would have talked about that earlier, but it's fine because now you know very well how neuronal networks work, right? And then it's an easier transition from there to convolutional neuronal networks. But okay, let's go per parts, right? We're gonna go do the recap as I usually do in the beginning of the lecture, so we can like make sure that we have everyone is in the same page. I got some questions about regularization techniques. Apparently, this idea of how the regularization is applied to neuronal networks is not entirely clear. So I'm going to give more details on that, how you can enforce regularization. Let me turn off the sound of this, of the people who joined the thing. Where is it? There. Well, yeah. And I'm going to give some extra debugging tips. Probably you already have some stuff that you experience on your own. So I want you to comment on that as well. So far, we have worked with a single optimizer. Which optimizer we have been working on, by the way? What's the optimizer that we have been using so far?
The GS.
The SGD. Yeah.
SGD.
Yeah, stochastic gradient descent, right? So like I'm going to show you the other options for optimizers because the SDG is the default pretty much. Everyone uses that one, but is by no means the best optimizer. And I'm going to tell you why. Then we're going to explore, like, we're going to go back to the tutorial. I'm going to tell you about like, so far we have been using just like S and X and Y of the 3 high data sets. Then you're going to see what happens when you use the whole data set. I did propose that some people could use that already for this proposed exercise, right? I said that you could use more features of the data. I don't know, apparently from the table that I have seen, nobody decided to do that yet, but we are going to see what happens. And then I'm going to show like how this model could be trained off with other optimizers. Then I also got some questions about interpretability, right? Because sometimes just getting the output of the model is not necessarily that helpful, right? You do want to understand how the features are correlated. For example, random forest does that for us, right? You can get the importance of the features. And I'm going to show you how you can do something similar in neural networks as well. And then finally, we are going to get to convolutional neuronal networks. I'm going to tell you a little bit about the components of convolutional neuronal networks, the main building blocks, which are the kernels, the padding techniques, and the pooling. And since I see that some of the papers that you listed there, they are also talking about classification versus not necessarily regression. And also some people asked about classification. I'm going to show convolutional neuronal networks in a classification context, okay? And then for that, we're going to use a different data set, which is the satellite image data set, so you see that I'm putting all these extra components that people have been asking about in this one lecture. So it might be a little heavy content-wise, but we can always try to touch on like some pending questions on the beginning of the next lecture as well. And then for the next lecture, right? Finally, I hope you got to read the message that I sent to you guys over the weekend on Slack, right? So the idea was to work on a special, is sort of a journal club. And for those who are not familiar with the idea of a journal club, it's essentially we bring papers that we'd like to discuss, right? And more specifically, papers that are using deep learning. So I can help you there, right? And why is that? Some people have sent me papers asking for help to understand the methods that are being used there, right? And I do realize, as I mentioned here, that many of those papers, they have some, the backbone is similar, right? So for example, the majority of them so far, they have been using convolutional neuronal networks. So we might benefit from actually discussing that in class, because then we can all like see how convolutional neuronal networks or any other type of neuronal networks are being applied like to answer different types of questions, right? And since the method is exactly the same, the backbone is exactly the same, we can get to see like how changing some specific components of these neuronal networks completely changes the type of application that you can do with that, right? So I think it's worth doing that. I remember that Sebastian at some point, he also asked about data batching, right? So we are also going to include that in this tutorial today. We are going to see how we can do data batching for this satellite data, data set. Okay, so hopefully like all the questions are going to be at least briefly touched today, and if not, we try to do that in the beginning of the next lecture. Okay, any questions about the plan? Any disagreements? Anything that you think could be different?
No, seems good and covering up all the requests, and let's see.
Yeah, there were just way too many requests, so maybe someone was left out because it's different to attend everyone in a single lecture, but we're gonna try our best. And if you feel like I didn't touch on your question, feel free to speak up, and then I try to make a comment or two about that. Okay. All right. So recap, right? Let me move the camera. Okay. So maybe I start here. On the regularization, right? So like we very briefly touched on the importance of applying regularization to the weights of the neuronal networks, right? And why was that? Anyone can mention very briefly why it's so important to make sure that the weights of the network, they're kind of distributed sort of in a uniform way?
I guess that we have to avoid that one weight dominates the other, more or less. I mean, that's how I understood it, but I only listened to the recording.
Right. Yeah. So we want that, right? So that's like empirically, that's what we're enforcing, right? We want to make sure that all the features, they are sort of paid attention in a fair way. So, and there are several empirical benefits for that. For example, you might have one of those features that are corrupted for that specific measurement that you took, right? And we mentioned some of the ways how you can corrupt the data, right? But more importantly, for the other side, which like the optimization side, we want these weights to be distributed because that enforces a very important property of our loss function, which is the convexity, right? And for those of you who remember what the convexity is, basically stands for trying to make the shape of this loss landscape to be as close to a bowl, right? So like to that regular bowl shape, because that one ensures us that it's we have at least a couple of options for a local minima that approximates a global minima, right? And if you find the global minima of the problem, that's for sure the point that has the lowest loss. But we might find local minimas or even local maximas that also satisfy the criterion for the minima of the problem, right? And because the criterion that we have been using so far, it's very sensitive. And which criterion was that? Can anyone remind us what was the criterion for the lowest loss? Was the derivative of the loss with respect to the weights to be equal to 0, right? Because that's by definition, that's the derivative in that point in the loss, right? For a given set of weights. And if the derivative is equal to 0, then we have the point of minima or maximum, right? But we hope for the best. So far, we have been just hoping for the best because we didn't have any way to ensure that that was indeed minima versus a maximum, right? Because the criterion is just too loose, it's too flexible, which the derivative is equal to 0. But today we're also going to see some strategies how you can perhaps like escape those areas of like local maxima or minima and try to even give like more flexibility to the model to find the effectively global minimum of the problem, which is when you're going to touch more options for optimizers. Okay, very well. But these kind of things we saw extensively with respect to logistic regression, right? So we had that extra term that was like lambda times the, I removed that slide. Anyways, was a lambda times the square, or sometimes just like the absolute value of the weights, right? And we have been calling that the regularization term. In neuronal networks, there is one more strategy that you can use, okay, which is referred to as the dropout, okay? So how does it work? So here we have a regular neuronal network, as you can see, right? So for example, just for the sake of like refreshing those concepts, right? If I say that this is the input layer and this is the output layer, what are those layers in the middle here?
The hidden layers.
The hidden layers, great. So for this setup, what's the dimensionality of my input?
5.
5, great. And given that I only have one node as the output, what type of problem is this that this network would be solving?
Regression.
Regression, very good. We also saw that like with a single node, I can also solve a binary classification problem, right? Where like this output could be either 0 or 1, right? If I have more classes, then I need more nodes. So like if you see a single node as output of a neuronal network, is either regression or a binary classification problem. Okay? Okay, very good. So one thing that people use quite a lot in neuronal networks is dropout, okay? So one of the ways how you can potentially enforce the network to stop depending so much on a specific feature, right? So again, the dimensionality of this data is 5, right? So that's like dimension 1, dimension 2, dimension 3, dimension 4, or feature 1, feature 2, feature 3, and so on, right? One of the things that you can do is to randomly drop some of these nodes, okay? So for example, in this setup, right, during training, instead of using all the features of the data, right, like to do the fine tuning of the weights of this network, to try to approximate the output or the target value that you're looking for, right? You can say that I'm gonna drop some nodes from a specific layer. So like this dropout rate is defined like per layer, okay? I'm gonna randomly drop with a probability P some of the nodes in that specific layer. And then I'm gonna try to make my model make a prediction using just this sparse selection of features, okay? So for example, here in this example, we see that those nodes in the first layer here, they were dropped, okay? So now I'm using just feature 1, feature 4, and feature 5, right? On the second layer, the first hidden layer in this case, right? I'm using just the combination of like features 1, 4, and 5, right? For this node, and the same for this node, okay? And they all learn different weights. Since the dropout probability for each one of these nodes, it's given by a probability, right? I might have a different combination of nodes in every time that I go over the data, right? In a new batch or a new epoch, okay? So you see that the combination of features that are being used and even the combination of hidden nodes in the hidden layers that are being used, they're constantly changing, right? And effectively, what's the consequence of doing that? For example, let's say that those two first features of the data, right? They could be highly correlated to some extent. Okay, so for all that matters, I don't need both features to make a prediction, right? Because they are correlated. So like whatever I learn from one, most likely I'm not gonna aggregate a lot of value by also considering the second feature, right? So potentially the network could say, okay, I don't need that feature specifically, so I'm just gonna assign a lot of weight to this first feature and very little weight for that one. The thing is that that information is not going to be available all the time during training, right? So you do enforce the feature that's coming from that other node to also be taken in consideration, okay? So by this way, you make sure that the weights that you have for that feature, it's not zero, right? And because this process is done like sort of in a random way, because there is a probability, you kind of ensure this property that we want so badly, which is like this sort of uniform distribution of weights over all the features and all the weights consequentially, right? Is that clear? How that can help us to achieve what we have been describing here in this scenario here? Any questions there?
So this one will help also to understanding the importance of the variable, I think, no?
Potentially, yes. So when you have this type of setup, right, we can use one thing that I'm going to show to you guys, which is called salience map, right, where basically you're just inverting the direction of information propagation in the network, right? Or you can use something else, which we are going to discuss as well, which we refer to as the Shapley value. But yeah, definitely, you can very well use these weights that we are training here in order to get like some understanding about the importance of the feature. Okay, but very important detail, you see that this probability, right, is only defined during training, right? Because like you want to drop that node during training because you want the network to be forced to always take in consideration all the data, and you use this dropout as a way of achieving that, right? But during inference, so like, okay, now this model is fully trained, right? You no longer want that, okay? So you want that node to be always present. And for example, one of the cool properties about that model.train and model.eval that we have been using all the time, right? So let me find my notebook here. I think it's this one, right? So if you guys recall, right, I told you like, okay, now you're going to start training, right? Move it to dot train. Now you're going to do the evaluation. So move it to dot eval. Where did I do that? Yeah, dot eval, right? And then when you start training, model dot train. So the dot, when you say dot eval, then automatically you're setting your network to evaluation mode, right? So you're just going to run an inference. You have no interest in fine tuning the weights. So when you do that, this probability of the node being present, it's automatically set to 1, independently of what you use for training, okay? So that ensures that the node is always available. It's always present in the network when you're running an inference, okay? So that's another cool thing that's included also in this switch between training mode and evaluation mode. Any questions on that? Okay, yeah.
Yeah, yes.
So yeah, so before we go to discuss the results, right? Let me just see. Before we go to discuss the results, another thing that you usually have to be careful with, and probably you have heard that in a different context, is overfitting and underfitting, right? So I don't know if I have covered that in this course. Did you or Longzhu cover that?
We have been covered it a bit when I was explaining random forest, that for the particular setting of the library package, the library that we were using, it was going in overfitting. So we were using 0.90 we were reaching, and in the training, sorry, and the testing was 0.6. So over there we were in a sort of overfitting. Then after tuning the parameter, the R testing, the R training were getting very close.
Okay.
So
Okay,
this was the kind of explanation.
So I'm just, okay, so I'm not going to spend a lot of time on this. I'm just going to cover very quickly, like in theory, what's the overfitting, right? So for example, usually you're associating the overfitting to the number of parameters that we have, right? So, and that's one of the dangers of just saying like, okay, so I observe that there is a trend, which that more layers that I use or more nodes that I use usually achieve better performance, right? So the intuitive, right? Your intuition there is that like the more the better, right? So you're just going to keep increasing the number of layers and nodes, making your models deeper and deeper and like larger, right? So for example, Google have realized that this is a quite successful approach. And now they have like models that have billions of parameters, right? So like we have been playing with like 4 layers, like 5 layers, right? Like up to like 1,000 nodes per layer. Google is using like millions of layers with like hundreds and like thousands of layers, nodes per layer, right? And like with a lot of recursion between those layers. So like first they have the resource to do so, because like otherwise you cannot train such thing in a laptop, as you can imagine, right? And for example, Sebastian was saying that like the training time for these models, even though they're very simple, right? You're using like 4 layers with like 1,000 nodes maximum, right? And you can see that the training time, it's already increasing quite significantly, right? So these models like that these guys are using nowadays, although they have a lot of capacity, so like the capacity of fitting the data is very good in general, right? They usually demand a lot of like computational resource in for a very long time. So these models, they have trained for weeks, right? But there is no free lunch, right? It's not because you're using more parameters, more layers and nodes, that necessarily are always going to achieve the best result, right? Because, for example, you guys remember that we have a training set and a test set, right? So if you use the training set to fit your data, right? If you have like a model with a low capacity, so let's say that you have like just 1 layer, right? As we saw, 1 layer or like 1 perceptron is capable of fitting just 1 line, right? So if you have a data that looks like that, and you try to use a perceptron to fit this data, right? The best that perceptron could do perhaps is to fit a line that sort of looks like this, okay? Now, we saw that when you increase the number of perceptrons, the number of like processing units, you're capable to approximate something that's slightly more complex, right? So here we would have like some sort of a polynomial of order 2, right? So now we can feed this data pretty well, right? Now let's say that like, okay, yeah, so apparently if I keep increasing the number of perceptrons and the number of layers that I have in this model, right? I can get even better accuracy, right? So for example, if you're comparing the mean square error of this model in this model, they both have mean square error equal to 0. Can you see that? Because like the difference between the model, which is the line, and the data, it's 0, right? I can pass like exactly through the points, correct? But if you have this model and this model, which one do you think it's the best one?
The middle one.
Why you think the middle one?
Because it covers all the data.
Right, this one also covers all the data, right? But why is this one better?
Oh, yeah.
Whereas some other point can fail.
Right, yeah. So like usually we have a specific word for that, which like how generalizable is your model, right? So for example, if I have one more data point, let's say that this data, it's following a trend, right? And that's perhaps like if I had more samples coming from these phenomena that I'm observing, right? Like, or getting more measurements, I would get more points that are around here, right? Hopefully, if this like it's a proper model, right? If I had more points, which now we're going to consider that those points, they are my test data set, right? Let me add a pen here. So like this guy here, right? If I do the prediction with this model that had like 9 perceptrons, right? For example, versus this one, the error in this one, it's lower for the test set than in this one. You see that the error here is going to be massive, right? And in this scenario, like we see that we have a perfect fitting for the training set, right? Which is represented by the black dots, but the error in my test data set is massive, right? And then usually when you're training your model, and that's why I plot both the training loss and the test loss, right? So you see that the training loss is going to look like this, hopefully, right? That's the ideal. That's what we are usually going for. And the I'm going to use the same color, okay? But and then the test set is going to look like something sort of like this. Okay, so the longer that you keep training this model, you're going to get better and better fits for the training, and the test is going to start like skyrocketing. Okay, and that's the by the book way of like identifying a model that's overfitting. If you see this, you can stop immediately and say like, this is overfitting. Okay, so that's one thing that you observe, like with respect to like this trade-off that you have between like achieving better and better performance in like fitting a model to the data, and what that actually represents in terms of like being capable of like extrapolating or making the prediction general for unseen or new points of the same data set. Okay. And then that's also like one of the reasons why instead of just keeping track of the excuse me, of the training loss, right? You also keep track of the test loss, because the test loss is what indeed matters to us, right? If the test loss is going up, that means that this model, although it's like achieving great performance here, it's going to perform very bad when I try to use or deploy this model like to actually solve a problem out there, like in the wild, right? Any questions on this?
Yes, Antonio, let me add in something. We were see very similar behavior when we were using random forest. So in the same way that we have a high value of hidden layers and node in neural network, we have the branching in random forest. So the default parameter was for each one node, one branching. So of course, everything was fitting in to reach that that point, that observation, and we were in this kind of overfitting. So we were, like Antonio was mentioning, the graph over there. So the concepts are very similar. We need to have models that are able to perform good and with the same level of R in this case for both training and testing. If not, our prediction, and that's why we make model, because we want to predict most of the time in spatial science in an unknown location. So it's going to be good in this area due to that we are not in the overfitting area. So try always to check this overfitting situation.
Yeah. Any other questions here?
I have a question. I was just wondering, because in random forest we use this cross-validation approach. That's not of use in neural networks, or?
You can do cross-validation, right? We just use as a proxy for cross-validation. We have these held out samples, which usually we refer to as the test set, right? But you see that that's applicable if you have, for example, like a really large data set, right? And that's why we say that like it's a big, that machine learning or like deep neuronal nets, they are meant for big data, right? Because if you say that you can comfortably just like put aside some samples just for the sake of like inferring or inspecting how the model is doing, that's already enough. If you have a smaller data set, you cannot just discard those samples just for the sake of validation sometimes, right? That's where the cross-validation comes at hand. But like, because we have a lot of samples here, we can just like take a chunk of it and leave aside just for test purpose, right? But yeah, They depend on how big is your data. Then you can use cross-validation. I have done it before.
Is it a minimum number you need to do the neural networks?
In number of samples?
Yeah.
If there is a minimum number, well, you guys are familiar with PCA at this point, right? Principal component analysis?
Yeah.
Okay, yeah. So the number of samples, I would say that's like has to be proportional to how much you can explain the whole variance of your data in terms of number of samples, right? For example, let's say that I'm gonna give you like 10 samples, right? The standard deviation, it's like 0.5, right? So like from these 10 samples, I have a standard deviation of 0.5. So if I'm trying to make a prediction with those training on those 10 samples, right? I'm gonna get like a pretty wide range of like outputs, okay? Is that enough, like as in terms of representation, right? With those 10 samples, I can, you tell me like with those 10 samples, that's everything that you need to know about the phenomena that you're trying to model, okay? Is that enough? Let's say that's it's a phenomena that can very well just be fit by a line, right? Let me give it like a more practical example here. So like, let's say that the data that you give to me are 10 samples that look like this. And so on, right? If you give me 10 samples that look like this, I'm gonna say, okay, 10 samples are enough to model this data, right? Now, if you say, I'm gonna give you 10 samples that look like this. Right? Are 10 samples enough? I would say no, you know? So it's very relative, the number of samples that you need, right? Let's say that if I had like 1,000 samples instead of 10, I would observe something that sort of looks like this, right? And then, oh, now I can see that there is a trend on this, okay? Because like I had like a huge variance on that data. So like you see that's like the number of samples and the number in the variance that you have for that data, they kind of go like side by side, right? So if you have like huge variance, a lot of variability in the data, you need more samples. That's how it works.
And let me adding also this, and just in this case, you know, the cross validation can help you understanding if you have enough data when you do the cross validation and you get a stable root mean square error. So if your error is stable, means that you are able with this number of data to capture all the variability of all the variants that Antonio was mentioning. So I always say, like, because this is coming quite often, this kind of question, how many points I need. In our geo environment, below 1,000, you are barely on the borderline. Okay, so if you start to have 500 points, because the variability is quite high, and you need more points to really track what Antonio was saying. So I use as a rule of thumb 1,000 points at least.
You see, that's very like domain related, right? Yeah. Like in biology, if you use 1,000 points, you can't do anything. Usually you're in the scale of hundreds of thousands of points. So you can start like understanding a trend on the data. So yeah, there are several factors there that play a role in like number of samples that you need, like the complexity of the system that you're trying to model, the nature of that system. So yeah. Okay. Any more questions on this before we go to the exercise? I think. Okay, yeah. So maybe we take a look on the exercise now, right? Let me see. This thing, it's right in front of me. How do I close this? Okay, exercise. So I'm very happy that a lot of people decide to do the exercise. was not really expecting so many people to do it. So yeah, anyone wants to make any comments about what they learned during the process of training these models with these different configurations? And if you did something different from, for example, what you're observing here. So maybe you can go first, Pepe. Did you observe anything interesting? Anything that you'd like to share, that like something that you
yes,
experience? Yeah.
So you really need, okay, apart of the learning rate, sorry, the processing time, that's why I stopped it, let's say, because I could not go there because the number of hidden layers increased, and of course the processing time was increasing. But at least in the first one, I was getting that the R was jumping quite a lot. Maybe the column number G is a bit the more stable one, G or H, but all the rest, you know, they were jumping with sometimes even in the same column, you were dropping even negative. And sometimes I also getting an error that was say something like, I cannot making linear model with all the points are in the same line for linear model or something like this. Now I don't remember the real.
Right. Yeah.
So that's why my question that is coming back from last time, if there is a rule of thumbs that we can at least select the, because if not, if we do all this training, it will be extremely long, the computational time. And of course, this is a data set. The Jedi is that for the 3i is a global level, so it would be billion, and of course start to training all this stuff would be impossible. So at least if there is a rule of thumbs, we concentrate in one number of hidden layer, number of nodes that is potentially good, and we play around that without starting from 1 to n.
Right. Yeah. So there are some stuff like I think I mentioned in the previous lecture that there is like a mathematical way of proving how many layers you need in theory to cover the complexity of the problem, right? Which goes in the same direction of what we discussed here. Okay. So like you see that there is a point, like a turning point, where increasing the number of nodes and layers would increase the likelihood of overfitting, right? But like in practical terms, and usually that's what you observe, is that, for example, in this, where is the, it's not book. Where's the figure of the neuronal net? Yeah, here, right? So let me open this. So there is a rule of thumb that most often it's what people use, right? So one thing that you can use is the, so for example, if you just want to go for one hidden layer, usually people recommend to use the mean of the number of nodes that you need for the input layer. So for example, here it would be 22. For the tree height data set, I think it would be 20, right? And then if you have one node for the output, it's 1. So what's the mean of 20 and 1? Would be like something around 10, right? So like that's one thing that people usually do. So like for a single hidden layer, you do like 20, 10, and 1.
So
okay.
20 put 10, let's say half of the number of 20, in this case 10.
Yeah, and then 1. Yeah.
Okay.
If you want to use more, you can use the same strategy. So like, for example, one thing that I'm going to show to you guys like during the convolutional neuronal network session is that usually you have this like sort of funnel, right? Like where you keep like decreasing the dimensionality until you get something that sort of looks like a cone, right? So that's something that has been shown to be quite successful as well. It's this strategy of like progressively decreasing the number of nodes that we have in the layer. Okay, but like, of course, that's always depend. The number of layers per se is something that's a little bit more empirical, but the number of nodes you can use this strategy, and most often it's like very successful. Okay.
Okay, cool. And for number of nodes?
Yeah, so for that's for number of nodes, right? Like this strategy.
Hidden,
Yeah.
sorry, hidden layer, sorry, yeah, other way around. Hidden
Yeah.
layers.
Hidden layer, it's a bit more empirical. So the number of hidden layers, like usually you start with something simpler and then you start increasing the number of layers. If like the performance is not good, then you add one more layer and then you go from there. But the starting point is usually something simpler, right? So for example, for the test that we have done, let me go back there. This thing is truly annoying. Yeah, here. So from the test that we have done, right, you see that like when you did the first test with a single hidden layer, right, you can achieve a good performance if you have more nodes on that single layer. Okay, but like in that, unfortunately, that's a part that's missing here, right? So let me see if someone did like more tests with more hidden layers. 3 hidden layers. Yeah, 2 hidden layers, right? Like things get way more stable here, right? So like if you start simple, like 1 hidden layer, you're gonna see that usually the performance is quite low, right? And then you either increase the number of nodes in that hidden layer, which might still get like a pretty bumpy loss output, right? But the more nodes that you increase and the more layers that you increase, more stable it gets, right? So that's something that you usually do empirically. Oh, this is a nice one with just 10 nodes, 80 nodes. Yeah. But the general trend that I hope you all can observe is that like the more complex that you make the model, and at least for like this constrained number of parameters that we're using here, usually better the performance gets, right? Or anyone tried something really crazy, like thousands of nodes with 500 hidden layers. I don't think anyone tried that, right? Yeah, apparently not. But that's where usually things get like pretty bizarre, because you're gonna see that like the R square for the training set is amazing. It's like almost 1, and then for the test set is borderline 0, which is like the effect of having this overfitting, right? Okay.
But when you want to introduce thousands of hidden layers, you have to assign them programmatically somehow and not type them one by one. Right?
Yeah. I mean, that's one of the things that I was mentioning to Giuseppe and Aphrodite before everybody else joined, right? Is that the way how we are doing this here is just for the sake of like being didactic, right? That's just for educational purpose, right?
Okay.
Like, but by no means you should be doing this. The one way how you can do that is like to pass one more parameter, right? Which would be like number of layers, for example. And then you can say how you want the number of layers to be the number of nodes in those layers to be a function of the number of hidden layers that you have. So for example, you can design a for loop that's going to create this little cone that we described before, right? So that's one way. Or if you just wanted to stick to the same number of hidden size for input and output, you could just very well say like, now create n layers that have this structure for me, right? That's a thing that you could do as well. Okay. This is just so you see like, okay, now I'm using 1 fully connected, 2 fully connected, and so on. Okay. Very well. Anyone else had like any comments to do with respect to what they observed during the test? So we have discussed that like apparently more nodes and more layers, they are more effective, right? Although probably you observe that there are other things, for example, the learning rates conditioning a lot how fast you go to this plateau, right? Where you have the lowest loss. So probably that's something that you have observed as well. So if you have a very low learning rate, let me see if I get one that has a very low learning rate. Like you see that like, okay, I have like a R of 0.55, right? But definitely there is room for improvement because like the loss was still going down. So in this case, like the learning rate is good because like the loss seems to be very well behaved, right? It's different from like, for example, we had some functions here that had like a huge spike. That's something that you don't want either, right? So like big learning rates, they are good because if the loss function, it's very simple. So it's like, it's very convex, right? If the loss function is very simple, a big learning rate might take you to the point of minima faster, right? But if the loss function is complex and you use like a very large learning rate, you might have something really bizarre. Let me see if I get one that's like really bad. Like this, right? You see like the loss is completely broken. And look at the output. It's not even like a number, right? It's just like everything's just being projected to one single point, right? So I hope you also got to observe that like the learning rate conditions a lot the way how you approximate the local, the minimum of the loss. Anything else that perhaps I didn't comment? Anything else that you observed?
Seems fine. Yes.
Yeah. If you haven't done this exercise yet, I highly recommend. And now you have even more reference because you can see on what your friends already have done, right? Then you can see that's like, yeah, okay, those samples, these combinations seems to be effective, right? But again, we have been doing that just for like few features of the data, which is just X and Y, right? So that's what we're gonna see today. Like, by the way, anyone try to use the whole data set instead of just X and Y? I mentioned in Slack that we could also do that instead. Okay, if anyone did, like now we're gonna very briefly discuss that. Okay, so this is exactly the same setup that we had before, right? The difference is that now, I don't know, I don't remember if we had done it before. Pepe mentioned that we had included in this data set also a variable called forest height, right? Which the tree height prediction given by a specific method, right, Pepe? Or a paper or someone who did that?
Yes, it was a paper. It's listed in my in the Data Explorer, one of the first Jupyter notebook of this exercise.
And what did they use?
The paper, they
to make
use
this
classification tree. Classification tree.
Classification tree.
Localized classification tree. So they divide in tiles and they do classification trees, regression trees every tiles, and then they combine. So they are the targeting is the average of all the R for each single.
Okay, yeah.
data.
But anyways, like what I wanted to see here in this very like simple test, right, was just like, okay, let's see how their model is doing, right? And that, again, this is the data set before Pepe did the cleaning. So you see that there are like some outliers here, right? But they should not deviate too much the R value, because the R value in the end of the day is like the combination of like most of the features, right? So you see that the R value that they're getting is 0.52. Okay, so that's essentially what's the value that we're trying to beat, right? Like we want to be better than they are, because that's part of human nature. We want to be better than others, right? So that's what we're trying to be better. Okay. How much did you get with random forest, Pepe?
We were around 0.7, but already with the cleaning data, I can
Okay.
check it out. Yeah.
Yeah. Anyways, right. So like random forest is doing around 0.7, right? Like, and we have seen so far that you're using just X and Y of the data, we get around 0.3, 0.35. Some people I saw there, right? I think the best that I got was also something around 0.4, right? But now let's see what changed when we try to use the whole data. Okay. Very well. So I think I'm using the wrong Jupyter notebook. Okay, yeah, that's the right one. I see that there is a message there. Pepe, did you upload this notebook?
Not yet. I will do
Uh,
it in the coffee break. Sorry.
Okay, yeah, so Pepe is gonna do that later, sorry.
Okay,
Yeah.
can you maybe just enlarge it a little bit?
Oh yeah, of course. Is this better?
Yes, thank you.
Yeah. Okay, yeah. So very well, yeah. So now we verified that the R value from these guys is 0.52, right? So now what we're gonna do is exactly the same that we have done before. So I'm gonna export the H, which is like the true value or what I'm trying to reproduce, right? Which is always important to emphasize. It's always also an estimate that's given by the combination of the 6 algorithms that Pepe described on his lecture on the random forest, right? And I'm also good. So I'm going to remove the H from my data, right? Because I don't want to train my network on the value that I'm trying to predict, because the networks, they are going to find out that it's a very good way to predict the tree height if I use the tree height as one of the predictors, right? So like you want to remove that variable from the data. And same thing for forest height. I also don't want to use this guy's estimate of the tree height as a parameter, because I mean, could be beneficial, but maybe they're just doing a poor job, right? But like we don't want to use their prediction. Then what we do next is our usual inspection of the range, right? So like now, I hope you're all familiarized already with like what are the variables that we have in this data set, right? So like we see that our X and Y are still there. Now we have extra variables here. Do you want to comment on the variables, Pepe, or you think it's always very well established by now what the variables mean? But if you have any questions about that, I think Pepe has like a little description of what each variable in this data set on his Jupyter notebook.
Yes,
well.
I can cover it quite fast in a fast way. X and Y we say lat long. Then the SVVI are vegetation index from satellite data. The tree cover is percentage of the trees in terms of canopy cover. Then Chelta are climate index. One is more temperature index and the other one is more precipitation index. Then all these one coming along, the magnitude convergence, northern and easterness are derived from morphological data, geomorphological data. So coming from digital elevation model, it identify all the, concavity, convexity, east and north, south exposition, where you have more accumulation of water. Then you have elevation, of course, and the same outlet. This one outlet and CTI are sort of flow accumulation values. So they identify how much up drainage and so on, how much water is bringing to the downhill. This one, the following up are all data from from soil data, the different kind of soil data. Anyway, again, in the Data Explorer tree height, there is all the list and explanation of this.
Very good. Yeah. So those are the variables that we're using, right?
Yeah.
Now you're going to use all of them instead of just X and Y. As you can observe, they are all in different ranges, right? Which for the sake of like training, they are not as meaningful as like a simple scaling between 0 and 1. So we can just very well do the scaling that we have done before, right? So like the tree height per se, we wanted to have sort of like a Gaussian distribution. So we are going to use the quantile transformation that we saw before, right? Nothing new here. All the other variables, you're going to do scaling between 0 and 1, which we also have seen before, right? So like, I hope there is no question there, but if there is, please let me know. Okay, so these is all things that we have done before. We are going to do our usual splitting, right? So like here, I'm reserving 30% of the samples for test, right? And the remaining 70% for training of the model. Okay. So here I tried a couple of different things, right? So like the very first thing that I tried was just like, let's see how the perceptron is going to behave. Okay. So like we have seen the perceptron not doing great for the just X and Y, right? But let's see how good the perception will do if we had like a proper data set, so like with more features associated to it, right? So just as we saw before, now we're gonna have the fully connected layer, the NN layer that receives input size, right? Now the input size before was 2 because it was just X and Y, right? So now my input size is equal to the number of samples that I have, correct? So here, I'm saying that the number of inputs is equal to data.shape1. Anyone with experience in Python can tell me what that is exactly? Again, data is this table that we just loaded up here, right? Is this data that we're plotting, correct? So data shape.0 is the number of rows. What's shape1? Is the number of columns, right? So the number of columns in this data now represents the features, right? And the number of features are the dimension. Therefore, the input in the NN layer, because it's the number of dimensions, is equal to the number of columns that I have. Before, we were just like setting manually, right? Because we only had 2. Now, let's say that you wanted to do this test for different number of features, right? Like, because that's one of the things that I said you could potentially try to play with, right? Not to use the whole data, but perhaps like a selection of features that you think it's more interesting to play with. So you could just drop the number of features that you didn't want to use, just the way how we did like the drop for forest height and, sorry, for forest height and age. You could just drop more variables that you wanted to discard, right? And then this script will directly be ready for you to use again, because the data.shape1 would be automatically adjusted for you, okay? The number of here there is a mistake, I put hidden, but like you see that the second parameter of perceptron is the output size, which is always equal to 1 by default, okay? Great, so now I want someone that's already very experienced to explain me what's coming next. What's happening here? So here we define the model, right? This is like a simple perceptron, right? That has input dimension as the number of features that I have in my data. And here that's the output, we're doing a simple regression. So you see that the output is 1, right? So like nothing new here. Then we are defining this, what's criterion? What is the criterion here that we're defining?
Aphrodite, for you.
Is it the loss function?
Yes.
It's the loss function that I want to use. Yeah.
Good.
I see that. Okay, great. Yeah. Now we're defining the type of optimizer that we want to use, which is
The stochastic gradient descent.
the stochastic gradient descent. Very good. And now we're going to try a range of like learning rates, just as we did before, right? So like here you see the list of like learning rates that I want to play. Very well. So you see that like everything else here seems to be just like as you saw before, right? So like those are the variables that I'm going to use to accumulate the losses, like for both training and validation. Here I set my mode to training mode because I want the gradients to be computed, right? So like I need all this extra information. Here I'm not using dropout. Actually, yeah, I think I didn't include an example using dropout. Well, I can discuss that later, but like if I had dropout, now the probability of the dropout is going to be taken in consideration. So you remember that I'm going to randomly drop some of the nodes, right, that we discussed before. It's one of the ways how I can enforce that uniform distribution of weights in the network, right? So that would say like, okay, now you can start dropping nodes randomly, right? Here, I get a prediction for the samples of my model, for the samples of my data, right? Then I get ypred. Here, I compute the mean square error between the prediction and the actual target values, right? Nothing new. Loss backward, what the loss backward does.
the differential equation?
Yeah, the gradients, compute the gradients for us. Optimizer step updates the weights based on the gradients, right? Nothing new here. And then the eval, it's like now I set my, I did one full pass in the data. Now I set my model to evaluation mode. So like all those things that were meant just for training purpose, they are like turned off. And then I can do a full pass just to see how it's performing on the test set. Okay. Very well. Now that we understand how the model is set, right? Any questions about how the model is set to be trained and evaluated? Any questions on there? There is nothing new, right? Like we didn't do anything different from what we have done so far and what you guys have done so far, right? But like, let's see how things perform now. So this is a perceptron, right? Just as we did before. The difference between the perceptron that we were using before is that it was just using X and Y before. And now it's using like all the 20 features that we have in the data, right? Look at how the R value changed just by using more features of the data. Like it's already a value of 0.5, right? But to look at the loss function is kind of like pretty random. Why is it happening? Like, why do we see so many jumps in the loss function, in this loss function? Potentially the learning rates.
I think because the loss function is very complex shape. So when it's jumping for all the different.
That's a potential explanation. But you see that when I change from learning rates 0.5 to 0.1, that goes away, right? So that means that, yeah, indeed, the loss function is complex. But in that case, the magnitude of the jumps that I was taking was just too high. So like, instead of like jump. So this is the helmet, right? So like, instead of jumping like from here to here and then here finally, right? I was doing that basically, right? I was jumping from side to side. And now, because I have a learning rate that's a little smaller, I can allow myself to just to take like little steps towards the point. That's like the ideal, right? So that's the difference basically. The learning rate was just too big. Okay. So now you see it's like, yeah, again, those are just perceptions, right? And you're just playing with the learning rate. So like for this one, 0.53, like this one, the learning rate was too small. So you see that like we didn't fully converge. So like the R value is not as great, right? But like, this is just a perception. It's like the simplest unity that you can use like in machine learning, right? And you already achieved 0.53. Just let's put that in perspective. What was the performance that we had given by their method? It was 0.52. And we are just using a perceptron and we already like achieve exactly the same performance that they had in their paper, right? So like, I hope you can appreciate like how much a simple model like a perceptron can do for you, as long as you have like a big enough data with enough information on it. Okay, any questions on that? Is that clear, like how the learning rates is impacting the shape of the loss? Everyone can see that? Great. Now let's see what changed when you go to the feed-forward network that we saw before. So you guys are all very, very familiar with that now, right? Because like that's essentially what you did in your homework, okay? So now we have more things to set, right? Which like, now I have the hidden dimension as well, right? Because the hidden dimension now is different from 1, because that's the number of nodes that I have in those hidden layers, right? So here I'm using 128, 256, and 512, right? Could I be using less? Most likely. Okay, so like that's something that I'd like you guys to play with as well. Very well. So I'm using exactly the same criterion as before, mean square error, right? And I'm using still the stochastic gradient descent. And that's the new range of values for learning rates that I'm going to use, right? So let's go very quickly over the results. So like now you see that, for example, this guy, right, using learning rate 0.75, it's like R value 0.58, 58, 58, oh, 59. Okay, it's getting better. Was there room for improvements on this guy? You see that like this loss is not optimal, right? Because like this point where it still managed to keep going down could be one place where the model would just like break, right? It got stuck like for a very little period of time in a sort of like funky, weird place, right? And then it managed to escape and like keep moving towards what we believe it's the global minima in this function, right? But like, yeah, that you also don't want something that looks like that, right? So if you can get like a loss function that, oh, this looks pretty good, like although it didn't converge, so you see that it was still going down, right? So probably like something that looks like that, but more epochs would be the best, right? And now we can see that like the cloud of points is getting sort of the shape that you want, right? Like a slope that's close to 1 and a value that's like around 0.6. Very well. So you can see that there are other options there, right? So like that was a model that had just 2 layers, right? So like the input layer, 1 hidden layer, and then already the output layer, right? So like we only had 3 layers there. Can everyone see that? What was the type of activation that I had in the hidden layers? ReLU, which maps my data. What's the range that the ReLU used to map the data?
Was it 0 to 1?
0 to plus infinite, right? So like it's,
yes.
yeah, it's not bounded on the upper bound. It's just like can be anything. But the output is bounded between a specific range, which is?
The tangent.
The tangent. And what are the extremes that I can get?
0 to 1.
It's -1 to 1, right? 0 to 1 is sigmoid.
Okay.
Is that the right activation function that I want for this data? Let's see what was the range of my output. I use the quantified transformer, right? So like the range of my output was between -1 and 1. So yeah, hyperbolic tangent is what I want to work with, right? I hope it's not like annoying that I keep coming back to these ideas. It's just because every time that I ask someone, answers something different. So like I want to make sure that everyone understands what those things are for. Okay, very good. So here you can see that like now I'm gonna do like a test using more layers, right? Then you can check on the results on your own later. Like there was a minimal difference. So you see that like at some point increasing the number of layers is no longer being helpful, right? So like we had like 0.6, right? Using one input layer, one hidden layer, and one output layer, right? Now I'm using more layers and like the results is not necessarily going up. And more than that, you see that the loss function got a little unstable now. You see? Can you see this? Ideally, this would look like some sort of like exponential decay, right? So like this is not good. So like maybe increasing the number of layers, you see, like this type of stuff for these data sets is not something that's like desirable. So there is a little bit of experimentation that you need to do there. But one thing that like we can see very clearly is that small learning rates are beneficial, right? So like usually you get something that's more well behaved with smaller learning rates. 0.75, like then not behaving that well. But luckily the loss function for this data, this is a very simple data set, right? So like the loss function for these data sets, like usually they all behave well. Okay. So let me move down a bit further. So yeah, I did a bunch of experiments. So once you get this Jupyter notebook, you're going to see that this table that I suggested to you guys, because I did the experiments myself as well. So like with even more variations than what I proposed to you guys. So I do my own homework as well. Very well. Yeah. So we have done all these tests with stochastic gradients so far, right? So I told you that there are several other optimizers and even more modern than the stochastic gradient. And that's essentially what we're going to do next, is to cover the other options of stochastic gradient. But perhaps we do a little break now, right? It has been an hour and 20 since we have been talking already.
Yes, Antonio, let's do some break. And meantime, I'm uploading already the files.
Yeah, I think that's a good plan. So we come back in 20 minutes?
Yes, let's come back at 35.
35.
Three.
All right. Sounds good. Yeah, so where did we stop? We stopped. So the last thing that I said is that we have been using just the stochastic gradient descent, right? Like as an optimizer, which by no means it's the state of the art with respect to best optimization techniques, right? There was one issue with the stochastic gradients that I think I mentioned like quite a bit, right? Which is with respect to what's the criteria, like what's is being optimized, right? So just as a recap, the stochastic gradient essentially computes the partial derivative of the loss, right? So here, which type of loss is this?
Mean squared.
Mean squared error.
Mean square error, right? So you're computing the partial derivative of the mean square error with respect to the weights, because that's what we can effectively optimize in the neuronal network, right? Everything else we choose a priori, right? We choose before we start anything, which that's why we call the hyperparameters. Some of the hyperparameters are like the activation functions, the learning rates that's going to be used, the number of dimension, the number of nodes, and the number of layers, right? So those are some of the hyperparameters. Those are things that are defined before we start the training, right? This is the weights and the bias, right? Because you guys remember that there is also a bias that we can include in the network, but like minimally the weights is the thing that we can optimize, right? And then we compute these partial derivatives, which essentially tells how much the error, or like the mean square error more specifically, is changing with respect to the small variations of the weights, right? And then we use that to do updates on the weights that we're going to be using for the next iteration, right? Very well. But in the end of the day, right, those updates, they are conditioned to this quantity here, right? Which is the gradient, right? How big is this partial derivative of the loss with respect to the weight, okay? And we said that we consider that the model has converged, or the model has achieved the point of minima, lowest loss for all that matters, once this quantity is no longer changing, right? With the partial derivative. Well, the partial derivative to be equal to 0, all that matters is that the derivative in a specific point along the loss is equal to 0, right? And then we said that that might give us like some problems. For example, in this curve here, if the starting point is here, the gradient here is pretty big initially, right? Because that's the derivative or the tangent, in this case, to this curve. So it's pretty big here. Here is slightly smaller, smaller until you get to this point, right? And like, if you can like remember the shape of the loss curve that usually we have, right? That's essentially what we're seeing there. So like the magnitude of the error is pretty big until it finally gets to something that's sort of a plateau, right? We didn't specify any specific stopping criteria, right? Like besides the number of epochs. So like so far, what we have done is like keeping iterating the model for 2000 epochs, for example, right? But you could very well just say like stop once you get to this point, right? Because like there is a chance that if you keep forcing the model to like keep updating the weights, you're just going to start diverging from like the point of like the minima, right? Very well. But in the end of the day, these updates, they're conditioned by this quantity, which is like the partial derivative at this point. If the partial derivative is 0 here, right, you see that the weights are no longer updating. Okay, so, and I hope you can appreciate that this is not the point of the actual minimal loss, right? The minimal error. Where is the minimal error for this curve?
Where the star is.
Where the star is, right? So like right now we got stuck here. Sorry, we got stuck here, and the desired point is this one. So what can we do to prevent that, right? One of the things is to run that like over batches, right? So like if you have a big enough data set, right, you should be able to like across all the samples where, for example, each one of these curves here, they would represent like a small subset of your data. Some of them might present these local minimums, right? But the loss landscape that's described for each one of these subsets of data sets that you have, they might have different shapes for the loss, right? So like if you overlap all of them, because in the end, you're just interested in one specific set of weights that fits its all, right? That solution for the whole problem. Like most likely you're gonna find that they all have a common point of minimal loss, right? So that's one of the strategies. And that's one of the things that we're going to see later on. And also something that Sebastian asked like a few lectures ago. Okay. So like the batching is beneficial also for like preventing getting stuck in local minimums. Okay. So like the data set that we are using, it's relatively small for the tree height data set, but that's definitely something that we could be using. And also like the loss is kind of simple, but like for more complex data sets, definitely batching is beneficial, okay? But that's not the only strategy that can be used, right? For example, if you compare this, let me go back here for just 1 second. If you compare this to a ball that's rolling down the hill, right? In this case, the gravity can be considered as some sort of gradient, right? Because like the acceleration of the ball is proportional to the gravity, which like by all that means, like for those that are more familiarized with physics, is the second derivative of the position of the ball, right? The first derivative would be speed, and then you have the second derivative of the position, which would be acceleration, right? So like by all that means, the gradient, it's also proportional to the speed, right? So very well. If you imagine that's a ball that's rolling down the hill, right? Once you get to the point where the gradient, right, like where the acceleration, it's no longer conditioned just by the gravity, right? Because at this point, the force that's pressing the ball like downhill in the opposition here is exactly the same, right? But we do have momentum to this ball, right? What's the momentum of the ball? The momentum of the ball is essentially why the ball that's rolling downhill doesn't necessarily stop immediately after it reaches a flat surface, right? So like the momentum of the ball is proportional to the velocity of the ball when the ball gets to this point, right? In its mass, of course. It's a product of mass and velocity, okay? So like observing that like the way how physics implements this kind of like optimization problem, right? Which like if we can indeed use this analogy, the ball wouldn't stop here, so the gradient descent shouldn't stop here either, right? It should have a little bit of momentum that perhaps if it's like a big enough momentum, right? The mass of this ball is like big enough, it could still like allow you to reach this point, right? Can everyone understand this type of analogy? Like what's the momentum of this ball that we're referring to and why it would prevent the ball of getting stuck in this point? And why the ball here could be analogy for also this sort of optimization problem that you're trying to solve?
I would say the mass would play a role, but
Can you repeat one more time? The audio was kind of...
I don't think the mass would play a role because the mass, when you go uphill, the same amount of energy will be drawn back from the mass.
So we're talking about momentum, not just mass, right?
Yes.
So like in this case, the mass is conserved, right? But the velocity in this point would be different from zero, right? So like, although the gravity would be zero here, so like the acceleration due to gravity would be zero, we still have momentum that's different from zero, which would allow this ball to keep moving, right? Very well. So like one strategy that people have employed is exactly to add this quantity that we call the momentum then, right? So for example, now we have this formulation here that has the usual first derivative, right? which here represents the traditional gradient, right? And we have one more quantity that's proportional also to the weights, okay? Which would play the role of like also computing the second derivative, which would be in this case, the velocity with which we are moving along the loss landscape, right? So what's the consequence of that? So for example, here we have the indication of the gradients, like in black, right? And in red, we have the addition of a momentum to it. So if we were just moving along the direction of the gradient, this movement of the loss, right, would be exactly like jumping from arrowhead to arrowhead. Okay, that's essentially what we have been doing so far. That's what the stochastic gradient would be doing for us. We'll be jumping like with this magnitude. Now we have a little bit of momentum, right? Which is like saying that I have something else, some sort of inertia to the way how I'm moving along the loss landscape. So it kind of holds me back a little bit. So it prevents all this like very large oscillation, right? I'm still oscillating, but I oscillate now with one parameter that's like this beta, okay? So now I have two parameters that I can define a priori. One is the learning rate, which is the alpha, which we're all familiarized with, right? Because that's the same that we have been using for stochastic gradient. And now I can add one more, which is the momentum that I want to add to this thing. So for example, let's have an intuition here. If the momentum is pretty big, what would be the consequence of that? First, if the momentum is zero, like how big would be this oscillation? If the momentum is zero, would the oscillation be bigger than the red line or smaller than the red line?
No, if you don't have momentum, it will be like the black line.
It would be like the black line. Not the black line, because the black line here are just the arrows, right? They're just indicating the direction of the gradient, but it would be like jumping from arrowhead to arrowhead, right? Yeah, right. So if I have a momentum, right, it decreases the oscillation. So if I have even a greater momentum than what we have like currently for this setup, I would have even lower oscillation, right? Can everyone see that? That's the intuition of how the momentum is acting to counterbalance this oscillation that the learning rate is implying. Okay? Questions on this?
Okay, this momentum is helping us to go one step further, a bit further than the zero rating.
And the zero rating?
Zero, when we reach the zero, the minimum, the local minimum.
The point, yeah, the point of like where the loss could be potentially zero, right? So it allows us to prevent getting stuck in a like bad local minima, right? That's the idea, or even a local maxima. Because if it prevents you from getting stuck there, right? Let's imagine what's the difference, right? Like, so for example, we had this ball that's rolling down the hill, right? If the ball is only conditioned by the gravity, the force of gravity in that point, when it reaches this state here, the vectoral force that I have on this object, right, is exactly the same that's like being offered by the floor, right? So in this case, I would no longer move. But if I have momentum, what happens? I reach that state, I go back, forth, and then blah, 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 right? Can everyone see that? So that's the intuition, right? So like, if this is the point that I want to stop, but this is a true global minima, what's going to happen is that I'm going to pass by that point, right? But I'm not going to explode and go far away, right? Like, I'm going to pass a little bit, but the direction of the gradients, the next step, are going to make me converge back to that point, right? At the same time, if like I was somewhere like here, imagine that this thing is continuous and it would continue in this direction. So like here, I could have like a local minima as well, or even a local maxima, right? So for all that matters, the derivative in that point could be equal to 0, and I could stop here because the criteria is satisfied, right? But it's by no means the place where I want to stop my optimization process, because the desired is here. Okay? All right, questions on this? Oh man, it's 52, right? Okay.
Quick question, Tony. How, I guess, like, how do you ensure that the momentum is large enough to, in the previous example, right, there was kind of like an uptick and then it went back down to the actual global or the global minimum instead of the local minimum. So how do you ensure that it makes it over that kind of, hill to then reach the actual global minimum?
So there are a couple of things. So for example, so far, as you can see, we have been dealing with like a constant for both the learning rate and the momentum, right? Which are values that we define a priori before we start the optimization, right? And then we have like, for example, empirically, we have these for loops, in which we go through like a couple of options for learning rate, right? But there are other methods that I'm gonna explain right now that they also use optimizations for both these constants, like the learning rate and the momentum. So probably I'm going to address your question in like 2 slides from now.
Okay, thank you.
Okay, yeah. So for example, some of the things that we have seen so far is that, for example, the learning rate, initially it's just a constant, right? And setting the learning rate, it's a little bit of art, right? It demands us to go like through several options for like learning rate, because like it's a constant that we have to set manually initially, right? So there are other methods, other optimization methods that remove the need of doing so, right? So some of them, it's this ADAGRAD, which use a adaptive learning rate, okay? And essentially what it does is to, instead of just using, so here, let me go by steps. Here we have the usual gradient, right? That's being computed with respect to the error and the weights, right? And that's the alpha, that's the learning rates that we had before. Okay, so nothing new. So this is the gradient, which like for the sake of simplicity, we're gonna say that's a G now, okay? So this G is conditioned by the error and the weights, okay? Now I can add a quantity that's like, I'm gonna say it's like the square of this gradient, okay? And I'm going to use the square of the gradient at every step that I take to also decrease the learning rate that I have, right? Because what we have seen before is that most often what you find yourself, it's in a scenario that looks like, okay, that looks like this, right? Where like after some point, right, keeping a learning rate high is not desirable, right? Because like the high learning rate is still being used to like increase or decrease. It's like a scalar for the gradient, right? And that could potentially even add some instability to this error, right? To this loss that we're computing. So why not also make this learning rate to change with respect to how big is the gradient that we're computing, right? So like the longer that you go, so you see that we're constantly adding the gradients, right? The lower and lower is this quantity here. That was like your initial learning rate alpha. And this quantity here, that's like getting smaller and smaller over time. So you see that the learning rate, if we say that this whole thing now is the learning rate, right? Is the adjusted learning rate, is getting smaller over time, which also helps you like to prevent you from escaping the ideal global minima, okay? There are several other small things that are also implemented by different optimizers, but for the sake of time, I'm going to skip them and go for the one that's like state of the art, which is Adam, okay? Both Adam and RMS prop, they are like considered the state of the art, okay, with respect to optimizers, because they do things that solve true problems, right? So for example, one thing that we, I think was Matt was asking before, right? Was like, how do I make sure that this momentum is also the ideal, right? And I told you that like the same type of question also applies for the learning rate. And an alternative that we have for that is to add adaptive learning rate. Okay, so like I have a quantity that I use to make adjustments of the learning rate as the training progresses, okay? So I can do the same for also the momentum. Okay, so now you see that I have two betas that I define. So now I have alpha, That's the initial learning rate to define, which is this quantity. And add-in also requires you to set the beta for both the momentum and is the, what was the M here? I forgot what was the M. I think M in this case now represents the gradient. I messed up with my notation here. Sorry, guys. But I think M represents the momentum. The M here represents the gradient. I think here was supposed to be a G. This big G. Yeah, but it has to be the gradient, right? So it has to be updated with respect to the gradient. So like it definitely has to be a quantity that's proportional to G here. I'm gonna fix this slides before I send it to you. Well, yeah, so those are two techniques that can be used, right? It's like the stochastic gradient, which like it's susceptible to this disadvantage, which is that like once the gradient is equal to 0 by all that matters for the stochastic gradient, you can get stuck in there. And then you have all these other optimizers that were created in order to address problems with respect to like the chance that you're gonna get stuck in these local minimums, right? And RMS prop and add-in, they are the methods that are more established nowadays that seems to be more effective in addressing that, okay? And how do we use this optimizer, right? So like, please, if you want to get more details about these auto optimizers that I skipped here, refer to these notes, and then you can also ask me for more details on that, okay? But just for the sake of time, let's move on to like see how we can use the add-in, okay? So I'm gonna use exactly the same backbone that we had before, okay? So like the script is exactly the same. The only thing that's changing now is this line. Before was SGD here, right? Which was the stochastic gradient. Now I only have add-in, okay? The difference is that add-in, let me show you like what are the parameters for add-in. You remember that there were two betas that had to be defined. By default, they're 0.9 and 0.999. Okay, so like those are the memories of the system with respect to both the gradient and the momentum. Okay, so the first beta, let's see if it says here. Yeah, the first beta, it's the proportional to the gradient, and the second beta is proportional to momentum, which is like the square of the gradient. Okay, so those are the two betas that you see here. All right, and they act as like adding this momentum that's helpful for preventing getting stuck in local minimums or maxima. All right, but like the beauty of this is the simplicity of like how you can very easily switch between optimizers. And then you have several other optimizers that you can do exactly the same, right? With like a bunch of things that are defined a priori that work pretty well for you. Now, everything else is exactly the same. So I'm going to skip this whole thing, okay? Let's see some of the training here. So you see that like for these learning rates, 0.1, and this hidden dimension, this model was not capable of training at all. So you see that like the loss is garbage, like the R value that was given was garbage as well. Now let's see, as we progressively decrease the learning rate. So like the learning rate now is being decreased. The loss still looks a little erratic, right? Like, so you see that's a little unstable, but after a little while, it managed to find like a sort of a point that seems to be approximating the minimum. Funny enough, and I hope you can see from there, you see that now we have these sort of spikes, right? And that's exactly where the momentum kicks in. Because like, if we didn't have the momentum, this thing would just like get flatter, flatter, and flatter until it just like plateaus, right? But because we have the momentum, like it slightly gets away from the point of minima, right? So like, imagine that you're going down and downhill. We pass by the point of minima, then we come back, you know, like, and that's essentially what you're seeing there. It's like this oscillation around the point of the minimum. Okay, and if you can compare to the previous results that we had, now we have the R value that's 0.60, so that's greater than what we had before. I think we got like 0.58 or so, right? Let's see what changed like when you start keep playing with the number of hidden dimensions and learning rate. This one was bad. Oh, 0.62 for a learning rate of 0.001. Okay, hidden dimension 128. Now, look at this. Look at what's happening here. The loss for the training set is still going down, while the loss for the validation kind of started plateauing here. Does it remind you of anything that we discussed before? I heard someone commenting something, but I couldn't hear.
Overfitting?
Oh, yeah. Looks like some overfitting was about to start happening here, right? Because the loss for the trainings is still going down, but the validation is no longer going down, right? And look that it's changed for this learning rate is slightly smaller here, right? Let's see if that keeps happening if we keep increasing the number of hidden dimensions. This one is bad. This one was still working well. Bad. Oh, for a bigger hidden dimension, this effect is even stronger now, right? Like visually speaking, right? So like the larger number of nodes in the hidden layer actually starts like making this effect of like overfitting even stronger, right? And it kind of confirms what we have seen before, which is like the more parameters you have, more likely you are of getting to a scenario where you're overfitting, right? Isn't that what we discussed earlier? You guys remember that? Great, yeah. So that's exactly like one of the things that we observe. So you don't want to be in this type of thing. I mean, until here, it's still fine, right? Because like the problematic point would be when you start getting a loss that starts increasing as you keep training. But like ideally, whatever you learn for the training should be directly applicable also for tests, right? So like this difference, if you can reduce that, is better. In here again, right? Although you see that the R values is still going up for the test set, because what we're plotting here is the test set here. So for this combination with a hidden dimension 512, right? And like learning rate 0.01, we achieved 0.63 already for R value. Okay. So like, yeah, so that's one of the, personally, Addon is the optimizer that I use the most, because like it's managed to train things pretty well. The strategy that's employed in order to explore the loss landscape is quite effective, because you have like this adaptation of both the learning rate and the momentum that you have for the model. Okay, any questions on that? I went pretty fast over the optimizers because I still want to dedicate like the rest of the class for convolutional neuronal networks. I want to make sure that I cover that before we discuss the papers. Okay.
Yeah, one point, the learning rate, we say that the learning rate in the Adam decrease. In the beginning it's quite big, and then it's decreasing, carry over the momentum, let's say.
Mm-hmm.
All right. So, but we don't need to set how much is decreasing this learning rate. Is it correct what I say or not?
I mean, we don't, it's set by default, right? That's what we saw here. By default, it has a value already.
Okay. So we are using the betas.
So, yeah, you're using the default. Yeah. And that's another cool thing, is that like the default works pretty well, right? Even though like you're using a learning rate that's can be anything, right? As long as it's like high enough initially, but not too high as well. Yeah, so there is a little bit of set that you have to do there. Like there is a delicate point of like where you should start. But for most applications, to be honest, that's the configuration that works the best. It's like learning rate of 0.001, right? 10 to the minus 3, and for those betas. And I think that's exactly the configuration that works the best for us here as well, right? Look. And when you tried something that was like slightly higher, we didn't even converge, right? So like it's really like this almost as Yeah, for the other one, it was too high. Yeah. So you could use something even smaller to start with, right? But apparently, if you go too high, here you still manage to converge, right? 0.01, 10 to the minus 2, right? But the others that were bigger than that, they didn't even converge. Okay. Any other questions?
Sorry, are you recording, by the way? I think you're not recording.
Yeah, it's going. It's going.
Is recording? Because
Yeah,
it's not
yeah.
red. Okay, thanks.
Yeah, for me, it says that's a recording. Okay.
Strange.
Okay. Questions?
Ah, now I found it. Sorry.
Okay. Yes, I think it was quite clear.
Okay. So very quickly, before we go to convolutional neuronal networks, I want to mention one thing, which like the shape values, right? So the shape this thing, I forgot to show the coolest part of like this whole optimizer thing. So what we're seeing here is this specific loss landscape, right? So like let's say that this loss landscape approximates a loss of a problem that we're trying to solve, right? Could be like mean square error or whatever. So we have two loss landscapes, those two here, okay? In each one of these colors identifies a different optimizer, okay? So one thing that I hope you can appreciate here is the difference in speed with which each one of them converges towards the point of like minima, right? In this case, they start here. And here we don't have a minima, right? Like a real global minima. We have a local minima, which like this settle point right here, right? So you can see that these methods, although like most of them converge towards the point of minima, right? They converge with different speeds, and also the oscillation changes quite a bit, right? So that's the stochastic gradient in red. In green is the stochastic gradient with momentum, right? So you see that like there was a huge acceleration while coming downhill, right? Because besides the usual gradient, you also have momentum now. So like the speed with which you come downhill is greater now, right? So you have this effect of like bouncing back on the water wall, but to also converge even faster than just the stochastic gradient. Can you see that? Right? And here we don't have the Adam, but we have RMS prop, which is very similar to Adam. So you see that like the trajectory of the RMS prop is like almost ideal, right? It cuts almost perpendicular to all the elevation lines of the loss. So that's pretty good. Now we have this thing. So like, for example, the settle point, right? The stochastic gradient, as we saw, it stops once the gradient is equal to 0, right? So like, if this was an actual ball, by no means it would ever stop here, right? And like, we are still in the pursuit of like a point with lower loss, correct? But like the stochastic gradient gets stuck in here. And that's something that we don't want, right? Like we want to keep moving towards the point of lowest loss. Okay. And as you can see, the stochastic gradient is the only method that would get stuck in there. Everybody else managed to escape that point. Oh no, actually the momentum took a little longer, but also escaped. Okay. Good. That's just like to exemplify what are the properties of each one of these methods. Okay. All right, finally to shape value. Let's do it. So as we discussed before, right? Like now we have these models that were trained and they are performing well, but sometimes we want to know more than just like a final output, right? For example, which features are the ones that seems to matter the most for that specific prediction, right? And random forest does that for us because it has one function, although I didn't have time to check specifically how random forest estimates the importance of the features. Do you remember from the top of your head, Pepe, how random forest does that?
Yes. So the decrease of root mean square error. So when you take out one variable, and for the classification,
so it takes out variables. That's how it does it.
Yes, it takes out one variable and it check how much is contributing the in and out. And for the classification, use the Gini index.
Okay. So I think it's very similar to the way how shape value works. I think the difference is that shape value, it's something that can be used for any model. And that's perhaps like the cool thing about this method, because random forest has its own way of like estimating the importance of features, right? But the shape value, it's this library from Python that I'm going to show to you like in a little bit, that you can give any type of predictive model, right? And that's the thing. For example, we could use that on random forest, or we could use that like on neural networks or absolutely any type of model that you have, right? And the way how it does that is slightly different from the way how apparently random forest does. Because in random forest, you take features out, right? And in shape, actually you add combinations of features, okay? So let's say, for example, just for a quick example here, let's say that you're trying to predict what's the income of a person based on 3 simple features, which is like the age, the gender, and the job, right? Like what's the current job of that person, okay? So let's see how those combinations will take place. The starting point is the average of all these observations. So like from this pool of people that we have analyzed, right? The starting point is the mean income, okay? And then what we see is that like, as we progressively add features to that sample, how that impacts on the prediction, right? So for example, you see that like from the mean value that you have, once we add what's the age of that specific person, we decrease the salary by 10,000, okay? And then if I add the gender, I decrease that salary by 2,000, okay? But the job increased that thing by 100,000, okay? So let's see what's the impact of adding just age, right? Initially, right? So like we can see like how age concatenates the information of those chains as we keep increasing the number of features that are analyzed simultaneously, right? So for example, here, that's like the marginal contribution of like a specific feature for with respect to the income, right? So for example, the prediction given this X0, which is like the sample that we're analyzing, and taking in consideration age is 40,000, right? And the prediction, the naive prediction for that sample, which would take just in consideration the mean income of all the samples that we have seen so far, would be 50,000, right? So if we do the same type of analysis for all the combinations in which age shows up, right, you'd have the difference between the mean, right, and just age, then gender and age, then job and age, and then all the other features and age, okay? So that's the contribution of the variable age for the overall prediction or the overall outcome, okay? And this, what you're seeing here is something that I didn't get much into the details, but it's essentially what game theory does, right? So what you're seeing is like what changes in the result of the game once we start removing or adding players, right? So apparently random forest use the other approach, which is like to remove players, right? And shape value progressively add players to the equation. And then you see how those players, they combine with other players in order to achieve an outcome, okay? So it's a very, you can see perhaps that when you have too many features, shape usually takes a very long time to process. So for example, that's not something that I see very often on neural networks, but because it's so intuitive, I thought that perhaps it's like worth to present. There is one thing that we use more often, which is called salience map, that I'm going to discuss like on convolutional neural networks, okay? And then just like for the sake of seeing how it works, right? So that's the library, shape, okay? That's we're going to import. Shape has one class that's called the deep explainer. So essentially what it does is to relate the model to X test. So that's our test data set, okay? And how these variables are conditioned to each other, this marginal condition, that's contribution that we saw here, is essentially what shape values are, okay? So the shape values, they encode the importance of those features for a prediction, okay? So just so we can see how it behaves for like 10 samples. So I'm just selecting like 10 samples from the test data set with its respective labels here, right? So let's see how it looks like. So here I did this training, right, for the shape values for this model that was trained. So here I'm just importing the previous model that was trained, which is this model, okay? And now I'm gonna see how this model, how the learned variables, the learned weights for this model, they are doing with respect to this little chunk from the test data set, okay? So here I'm just plotting like prediction by true value, right? So we see that like, yeah, the model by itself, it's predicting something that seems to make sense. The R value is 0.82, right? So like, it's like doing a fair job, right? Now, if we take a look on the shape values, which as we saw before, they are a proxy for how important those features are, right? The one that comes out first is the X, is the latitude, okay? I don't know, Pepe, if you have like, what were the importance of the features that were delivered by random forest, but that's something that you guys can do later on as well and try to compare like what Shep says is important versus what random forest is saying is important, right? Then you have these other S bios. What were those again? S bio?
They were climate, precipitation and temperature related.
Okay. Does
So
it make sense that it seems to be deterministic to predict?
Always,
Yeah.
yeah.
Then in fourth comes the longitude. So it
Yeah.
seems to make sense to some extent, right? But this is kind of general, like we don't know exactly in which direction this contribution is happening, right? So for example, the greater the latitude, does it necessarily implies in higher or like bigger trees or the other way around, right? So like, then you have this other plot that's called the force plot. That's also given by Shep values, right? Where now you can do the inspection of like, okay, given this feature, right? In which direction it's steering the prediction, right? So for example, you see that the height tends to push the tree height prediction to higher values, right? The latitude, sorry, the X tends to push the tree height prediction to higher values, right? And the Chelsea bios seems to be doing the other way around, okay? This is for one specific sample. So for example, I'm doing this analysis for this sample number 2 from this chunk of the test data set that I got, right? So I had 10 samples that I selected here, right? And here I'm analyzing the sample number 2 from like this set, right? So I can do exactly the same thing per sample that I have. This is the overall, so that's why they call it the global interpretation of the model, right? And this is like per feature. If you want to see like, okay, for this specific sample, I had a prediction of like 10 meters high tree, right? But how those features were combined. So that's something that the Shep value can do for you, okay? And then you have other stuff as well. So like here you have like the combination of all the 10 samples, right? And then you can see how those features were combined. So for example, if you just move your mouse around, you can see what was the respective importance of those variables, right? For each one of the prediction for each one of those samples. And that's exactly the same thing that we saw before, right? Here, what we're seeing is that, for example, this 0.013 is the mean of all the trees, okay? Remember that is the mean after the quantile transformation, right? So like at this point, the distribution of tree heights is still some sort of Gaussian, right? So you can also do the inverse transform before you do this analysis. But the mean there was 0.013. Then you can see how each one of these variables, they steer the final value in specific directions, right? So you see that, for example, the latitude here was pushing towards like the right, which is like goes towards like higher values, right? Therefore, higher trees. And then you can see how the other variables are pushing in different directions, which I think is kind of cool. But again, that's like something that's helpful when you're talking about a data set that doesn't have that many features, right? If you had like 1,000 of features, like this type of visualization wouldn't be that informative anymore. Okay. So that's just to let you know that there is such thing as shape values that you can use to try to interrogate your model, like, and try to extract more information about how these predictions are taking place. Okay, so that's almost like a parenthesis on what you're doing, just so you know that there is a way to
Yeah, very
see.
cool, this representation, and is really informative. So it's trying to not to be so much black box.
Exactly. Yeah. Yeah. So you know that like how those features are being combined. Good.
So, and Tony, in this case, what that means, so as the latitude increases for this sample, that has like an impact of, I guess, what, like 0.33. Is that like an actual increase in the height of like what you would expect to see in the sample?
Yes, but remember that this is like after the quantile transformation, right? So that's not in meters necessarily.
Right.
Yeah. So yeah,
Yep.
but that would be directly impacted on like the prediction. So for example, the information of the latitude would be adding 5 meters to the tree heights in general. You see? Yeah, that would be the idea. I think there is a question here.
Yeah, about whether or not X is longitude or latitude.
I think it was latitude, right, Pepper?
No, a Y is latitude. But anyway, don't worry.
Yeah.
Yeah, I
Okay,
think
yeah.
everybody knows it. The meaning.
All right. As you can tell, I'm not from geography.
Okay, cool. Yeah, very
Yeah.
informative.
So Alonso is asking, how do you read the red? So the red pushes you to positive, so like greater values, and the blue is towards smaller values. That's how it works.
So this means also positive correlated, negative correlated. Yes.
Yeah, yeah. You
Yeah.
can understand as such. Yeah. If you say that's like positive correlated is like, yeah, by increasing this value, I increase the outcome. Yes.
Yeah.
Mm-hmm. Okay.
Okay. Cool.
Good. So let's get to convolutional neuronal networks in this little bit of time we have. We have 20 minutes. That's right.
Yeah,
Okay.
something 45. Yeah, 20 minutes.
Right. So can we solve image processing problems with the current neuronal networks that we have been working with? What do you guys think? Because so far we have been working with table data sets, right? Which is like I have the number of observations, right? The number of samples that I have as rows, and the columns, they represent features. So that's a table, right? Could I solve something that has a spatial pattern as well? So they're not just independent like samples, but they actually represent something that's like has a spatial organization using neuronal networks. What do you guys think?
Yes, you can.
Someone said yes.
Yeah, I said yes.
Yeah. Okay. Yeah. So yeah, you can, right? And people have done that for quite a long time. So maybe we do that now. Let's see how that would work. Okay. So now you should have like one more notebook. So today I'm going over 2 notebooks with you guys. This one is the one that has the head using multi-layer perception and convolutional neuronal networks. Okay. So for this test, like as I said, we want to see if we're capable of like using the simple neuronal network first to analyze a problem that's like image based, right? So for that, I'm going to use this data set that's called the set 6. And there is also a set 4, which like for the difference between them is that set 6 has 6 classes of like images in the satellite data set, right? And set 4 has only 4. I'm going to do the tutorial on the set 6, right? And what are the types of like land covers that you can find there? So the zeros, they represent buildings. I plot it here. So zeros are buildings. So here it's like an image of a building. And that was the only one in this sample that I plotted. One is barren land. So let's see. So here we have barren land here too, and also here, and so on. So like those are the others. Here we have just waters, we have road, grassland, and trees, right? Very well. That's how the data set looks like. Feel free to play with that later, okay? So the size of the image there consists of like 28 pixels by 28 pixels, okay? And the bands here, they are 4 bands. It's red, green, and blue, which is the usual RGB image. And that's what I'm plotting for you guys here, is like the colorful image. And I have one more band that's the infrared, okay, which I'm not showing because like it wouldn't be that meaningful for me, but like we are going to use for processing, okay? Very well. So that's the data. So like the data is like this 28 by 28 pixels, 4 bands, RGB, and that's the number of samples that we have there, okay? Which like slightly bigger than 300,000 for training. And then this data already has a chunk that's organized to be the test set. So I don't need to do the splitting as we we're doing before. I have a segment that's just meant for testing. And fun enough, we actually have competitions on who does better on this data set. You guys should definitely check out like the Kaggle website. And maybe that's gonna be the assignment that I'm gonna grade. I'm gonna grade you according to how good you do in the prediction. Okay, let's see the code by itself now, right? So you see that I'm importing the torch, which is essentially the way how I design the networks, right? You guys are familiar with that, NumPy. The packages should be all familiar to you. Here I'm loading the data set. So you see that I'm loading the set 6, right? I'm loading like training images as being the training X, the labels, same thing for this data set. Here I'm just plotting the dimensions of this data, as you can see, right? So like the labels, they're organized as like one hot encoding, right? So that means that, for example, I have the 6 labels, as we saw before, and I have one just for the column that identifies the type of class, right? So for example, here, as we see, for the tree, the image that contain trees, I have one just for the number 2, right? So 0 was building, 1 was barren land, and 2 was trees, right? And 5, I think, were water, as you can see here. Or maybe you cannot see because the image is so pixelized, but yeah, very well. So that's just like data organization, okay? So now let's see how we can do this task with respect to, first let's create the data set, like the batching, right? So here what I did was to create one class that I'm gonna use to do the batching of the data, okay? So this one class is gonna receive samples, right, that are coming from the data set. And then I'm gonna select a chunk from that data to be one batch, okay? So what does it mean? So for example, here, I'm gonna select batch size of 1024 samples. So initially the whole data set had like 300,000 samples, right? I'm gonna select like a small portion of it just to speed up the training process. So I'm not going to use the whole 300,000, right? But I'm going to use just 50,000, okay? So those are the samples that effectively I'm going to use to pass as like the input to my data set. I'm going to create a data set that has 50,000 samples, okay? So now every time that I select one batch from this data set, I'm going to select a subset of 1,024 samples. Okay, and that's essentially what my data set is doing. Okay, everything else here should be familiar to you. So for example, you see that the data, we're still transforming that to torch float. So I think Pepe asked me that like on the previous lectures, why we have to transform to that. And that's the answer is still the same. Like we transform to torch because that's the input that the torch library expects. So like it goes from NumPy to torch, and it's floats because we need to be decimal, right? So we can do computation on that. And this is all like very simple stuff, very well. Here, those are the indexes, right? So like among the samples that I use for the test data set, right? For the data set, right? I'm gonna select a small sample that I'm gonna use for validation purpose, right? So like now I have test data, training data set, which corresponds to 80% of the samples, okay? I have a validation data set that corresponds to these 20% samples that are coming from the whole data set. And I still have a test data set that was given to me directly by the people who built the data set, okay? So for example, instead of doing cross validation, because I have so many samples, I can allow myself to just like partite the data set in 3 chunks. One of them is already given to me. Another one is like a substantial amount of samples that I can just split in like 2 small sections, one for training, another one just for validation purpose. And then if I say, okay, now I would be running on a real test scenario, right? Let's say that I'm going to deploy this method for like to be used out there in like for satellite images. Then I can use the test data set to do this kind of evaluation. And that's the test data set that people use to report the results in the competition, because that's a truly unseen data set, okay? That's just small details, okay? So now we have this sampler. So the sampler essentially tells us how I'm gonna sample samples from the data set, okay? So like among these 50,000 samples that I had, how am I gonna choose the samples from this data set, right? In order to compose this subset of samples, which is the batch of 1024, okay? So like I'm gonna do that in a random fashion. So like this is the way how I'm gonna sample samples from the test data set. So what would be the alternative of doing that, right? You could say that I'm gonna just sample the samples from the data set in a sequential fashion. So for example, I'm gonna go from 0, 1, 2, 3, 4, 5, like the index of the samples, or I'm just gonna like randomly sample samples from the data set, like in a random fashion, right? And that's essentially what the subset random sampler does. So like from the whole set of potential samples that I can get, I'm gonna sample some like in a random fashion. It's a little convoluted because sample from like selecting a sample and like sample observation, they have the same word here, but I hope this is not too confusing for you, because I'm just saying sample, sample, sample. Is that clear? Like, is there any question on that? I lost my band.
I actually have a question, but it's more related to, can you have repetitive sampling, in a sense, taking one observation 2 times?
Repetitive sampling. So
sorry, that the choices that you can get selected more than once into the sample, so to say.
Yeah, so I think the subset random sampler, let's see what's the default, but I think it includes no repetition. PyTorch, let's say here. Generator. Yeah, is the replacement. That's the thing that I was looking for. So without replacement, right? So that means that in theory, you could select the same sample twice, because the replacement would prevent that, right? Samples are drawn with replacement. If not, they're drawn without replacement, which means that when a sample index is drawn for a row, it cannot be drawn again for that row. Yeah, that's correct. Yeah. So like if there is replacement, right, that means it cannot be drawn again, right? But here it's without replacement. So in theory, you could select the same sample twice. Okay. Whoever asked the question,
yes,
does it answer right? Okay. Yeah. Okay. Cool. Very good. Any other questions on that? Is that sort of clear? Like we are creating like mini chunks of the data that's now they're composed by like 1024 samples, right? And that's how we're gonna go over the data, like in these sub chunks, instead of using all the samples all the time, the way how you're doing before. Okay, so that's how you batch your data, with something that we discussed before that like could be helpful, right? For the sake of the optimization, because sometimes the loss function that's defined, for this curve, it's slightly different. Like each curve here is defined by the batch, right? So if you have several batches, each batch could have a slightly different curve. So if you superpose all these curves, most likely, like that's usually the case, the point of minima for all of them overlaps. So even though you could get stuck for one mini batch, the other mini batch will still push you to converge to the right place. So that's a way that also prevents like getting stuck in local minimas, is to use batching. Question. Okay. All right. Let's keep going then. Okay. So now I'm going to define a simple linear feed-forward neuronal network, right, to do the classification of those samples. Okay. So can anyone help me to read the way how I'm defining the feed-forward neuronal network for this classification now? I start by defining the layers, right? Which was exactly what we did before for the feed-forward neuronal network and also for the perceptron, right? So what the linear layer does. What's the first value that I have? Don't worry about the number by itself. I'm going to explain 1 second what the number is, but what's the first parameter that I give for the linear layer?
Those are the input nodes.
Is the dimension of the input, right? So like we know that the input, they are images of 28 pixels by 28 pixels, right? By 4 channels, right? Which is red, blue, green, and infrared. How much is this? $3,136, right? Which is exactly this number that we have here. So what we're doing essentially is to just flatten the whole image, just the way how it's suggested here, right? So we get an image and we flatten it, like including the channels. And then we use that as input for the model, right? So that's a way how we can use like a feed-forward neuronal network to classify images. Okay, any questions there? All right, so we move on.
Ask a question, sorry.
Yeah, of course.
How's the output then defined? 1,000, where's that coming from?
So again, right, like we're defining here 4 layers, right? The first one is always inputs, the last one is always output.
Yeah, got it.
And those are hidden, right? Yeah. So that's the dimension to the hidden. So like then we project like 1,000 to 1,000. So that's like the first hidden, second hidden, and then the last one is the output, right? So now first we only had 1 here, right? For the previous networks. Why do I have 6 now?
Rest is different classes.
Yeah, it's 1 per class, right? We said that like if you have 1 node in the output, is either because you're doing a regression or because you're doing a binary classification. Then you can allow that node to be either 0 or 1. But if you have more classes, you need 1 node per class. That's how it works. Okay, and we have 6 classes here. Okay, then what happens? What's gonna happen here? So X in this point is a batch of images, right? So like it's gonna be like a set of images. Then I pass it to the first layer. The first layer is gonna transform this like number of samples in the batch, which is 1,024 by number of features. So it now has 3,136 features because I'm gonna flatten the image, right? So you can do this. So I can use a feed-forward neuronal network. like the activation of the intermediary layers is our friend ReLU, right? Then I pass to the second layer, ReLU, third layer, ReLU. And then here, I'm not using any activation at this point, right? I defined, but I'm not using, okay? So then it goes directly to output, right? So I'm not imposing any kind of constraints on the output at this point. Can everyone see that? That like it could be going from minus infinite to plus infinite. So, okay. Very well. Now I did a slight modification on the training script. Okay, so you're gonna see that like, although the functions are exactly the same, so you're gonna see the optimizer, zero grad is still there. Loss backwards is still there. Optimizer step, everything that we're like familiar with, they should all be there still. There are like just small changes here because now train became a function, right? Where I pass like a model that I want to use. So I'm going to define a model like outside. I'm going to say what's the criterion, the optimizer, and I'm going to pass both the train loader and the test loader and number of epochs that I want to use. Okay. And then this whole thing is going to happen within this function. Okay. And then I also have a evaluate function that's going to be called like every 10 epochs, just so I can see how the model is doing, both in the train data set and the test data set. Okay. All good. One thing that's going to be slightly different is that now we are doing a classification, right? Can you use mean square error for a classification? What do you guys think? Well, for the sake of time, no, you cannot, right? You need something that identifies like how well you're doing with respect to all the classes, right? There is no single quantity that you can approximate with a mean square error. So one thing that you can do is to consider that you have two distributions now for each sample. So one sample has a distribution of how good is the fit for each one of the classes, right? So let's say that's like, we're gonna have this output in terms of probabilities. So for example, for one sample, let's go back to the samples here. If I give you like this one sample, let's say that it had the probability of being barren land of 1%. It had probability of being roads of 2%. It had probability of being trees because like it's kind of similar, right? It had probability of being trees of like 10%, but it still had 89% of chance of being water, right? So like you see that there is a probability over the classes, right? You see that there is a probability distribution over the classes, where like the peak for probability is on the correct class, correct? But it is a probability distribution. Can everyone see that? Okay. Well, let's go back here. So what I'm saying is the following. Let me make a little graph here. Let's say that's like I have, those are the index from the satellite image that goes from 0 to 1, 2, 3, 4, and 5, right? So those are the six classes, okay? That image that I showed to you guys was water, right? Which has the index 5. Okay, so I'm going to refer in terms of indexes instead of writing water here, just for simplicity. Okay, the probability for that image here of being road, it's very small, like, because like there is a very low probability that we're going to classify these as being road, because there is nothing here that could remotely resemble road, right? These at least has like some parallel lines, so potentially you could misclassify that as being road, but like not this, right? So like the output of my model, if the model is properly trained, it's going to be like something that's probability here, right? It's going to be something like small, potentially like a little higher for one class specifically. But when I get to 5, I expect these probabilities to be pretty high here. Okay. But for all that matters, if I sum all these guys, right, the probability of being 0, the probability of being 1, the probability of being 2, these all should sum to p equal to 1, right? Because there is no chance that I have a image that's not belonging to one of the 6 classes. Is that sort of clear to everyone? Because this data set has only images from 6 classes. So there is no chance that I have an image that's not from one of those classes specifically, okay? But like for all that matters, this is a probability distribution. You see, where that I have a probability distribution over the classes, okay? So what I can do is to say like, this is the output of my model, right? This is what my model can predict. So my model has like a little bit of confidence, like with respect to the classes, with like the majority of the confidence that my class belongs, my sample belongs to this class, okay? Now the true distribution that's coming like from my ground truth, right? It's gonna look like this. So like I have 1, so this is 1. This is p equal to 1 here, right? It's 1 for that class. So I can compare this distribution to this distribution, right? So like if this distribution is exactly like this distribution, then my model is doing a great job, right? Because my model can precisely replicate the true distribution of my output, okay? So if an alternative scenario, let's say that it was actually looking like this, okay? So this distribution is very different from this distribution, okay? So I can use this difference between distributions as a way to quantify how good my model is doing. Can everyone see that? Right? So like if those two distributions, they're exactly the same, the model is doing great. If those two distributions are different, the model is doing poorly, right? And the closer that one distribution gets to the other, right? So as I keep like optimizing my model, the closer that they get, lower is this difference, and therefore I can optimize that. I'm still optimizing a loss, right? I'm reducing the loss, where the loss is referring to how different those two distributions are. Okay, and that's cross entropy. Ta-da. That's what cross entropy does. It's like it's the difference between the two distributions. Okay, I know that I'm rushing a little bit. So we can always review those concepts like in the beginning of the next lecture. But I just want to get to the point where you can see at least how the feed for neuronal networks is going to do on the image data set. Okay, so very well. So that's essentially what we are doing. Like when we say that now my loss is cross entropy, so computes like the difference between two distributions, right? The output now, it's a probability distribution over classes, right? So as you can see here, the output's a probability distribution. So like it has small values like for each one of the classes. And then the point that has the maximum likelihood, right? Which hopefully is going to be this one. I say, just give me the point or the class in this case that has the highest likelihood. So in this case, it would return 5 for me, right? And in this case here, like for the second curve that I'm showing, it would return 2. That would be 2, right? And that's essentially what I'm doing here. I say like, just give me the index of the point that has the highest probability. So like the class that the model think it is, right? And then that's how I'm going to predict the accuracy, because I'm going to compare the two targets. So like the real labels that are given by the predicted labels. And then I'm going to compare like, okay, from the total, tell me how many times you got it right? So that's accuracy. That's what we're going to report. Besides the usual loss. Okay, very well. So that's what we're going to do now. So you see that we have a range of learning rates. I'm going to use the optimizer Adam, which we just got to learn about. The loss now is cross entropy because I need to compare two distributions, right? I hope that's sort of clear to everyone. And that's how my model looks like throughout the training process, right? So I'm training just for 100 epochs. You see that the loss was too small, so like it sort of seems to be plateaued here, but it's going down, but it's just going down like in smaller numbers, right? But the accuracy is going up over time. So like it starts in 74, 90, it oscillated a little bit to 71, and then it finished like around 93% of like accuracy for this model, right? But that was training, but you see a similar trend on test accuracy. Okay, then you can see how it performs for other configurations. So for example, here I was using learning rate of 0.01. Here I decreased to 0.005, right? So like I got 94.05. This one, the best one was 93.37, decreasing even further, 94.29, right? So you see that like, yes, we can say that the feed-forward neuronal network can learn to classify the image with accuracy that's relatively high, right? So you see like 94% of accuracy for the classification of the samples in the test data set, right? So it can do a good job. Usually things get more complicated when there are more like significant spatial patterns that you need to pick up on, right? Because right now what we're doing in this data set is simply like getting each one of these samples, right? And classify them as belonging something. So for example, the bearing length, if I just take in consideration the color of this, I would have a pretty high accuracy already, right? Because like you see that the color is very stereotypical, right? Also the water is always blue, right? So like if I just take in consideration color, mean color, I should have a pretty good classifier already. So like there are hacks that the model can use. So for this data set, a feed-forward network is already doing the job pretty well, right? But like when you have a data set that has more complex patterns, then you need something more specific. And that's where we're going to get to convolutional neuronal network, because convolutional neuronal networks, they're better to get to these patterns. But unfortunately, I'm going to have to leave it for the beginning of the next lecture. I think I'm just too slow. Like I always run out of time. But yeah, so
it's good. In this way, we are able to get the most essential part of the lecture. Okay, thank you, Antonio. And yeah, we can close up the lecture today a bit longer, but I think it was important to cover up also this part. And see you on Thursday with the final lecture. So we will have a convolutional neural network, a bit of discussion, and then a closing up of the course of the lecture.
Yeah.
And we will have the wiki material.
So until this point, I only have 3 papers there to be discussed. So if you have more papers to be discussed, if we have only 3 papers, we can discuss all the 3, I think, because they have like similar.
Yeah, 3 are.
Yeah.
Maybe another 2, something. If not, they become too much. Too many.
Yeah, if we have more, then we need to vote, right? But remember that like it's gonna be journal club style. So whoever proposed the paper is gonna introduce the paper, and then I'm gonna help with like understanding the methods. So prepare a little presentation so you can introduce the paper.
Okay.
Also you, Pepe. Yeah.
Okay, thank you, and see you on Thursday.